start this please. We are waiting. Please start this. इसको मैं फुल स्क्रीन कर दूं? जी। Okay.
ये तो बंद किया हुआ है
छोटा सा हुआ लेकिन हमारी रिकॉर्डिंग आ रहा है यस यस
Start it.
I think this one is
Let's start. Hello everyone, thank you for coming to my talk. Today I will talk about some results that I obtained with a group of researchers. These results are about graph theory, and they were published in a couple of conferences and in one journal paper. And so over here, I'm trying to summarize those results. So I will, first of all, I will give some definitions that what is this problem and how we can compute it in some sense. And then I will try to give you the results that we obtained. Today, I will not try to go into details about the proofs of these results because these proofs are quite, of course, they require a lot more time to explain all of those things. And so I will not go into much details, but I will just give you an overview or an outline of these results. So let us start. So we start with, so this is basically, this is the problem for graphs. So we say, suppose I have a graph G, and this graph G has a set of vertices V and a set of edges E. It's a simple graph, so that means that we are not talking about graph with loops and directed graph and so on and so forth. So it's a simple graph. In this given simple graph, I say that a dominating set is a subset of vertices in this graph, such that all those vertices which are outside the subset have a neighbor in the set D. So for example, if D is the dominating set, and that D is a subset of vertices, then every other vertex which is not in D has a neighbor in D. So this set D is a dominating set. For example, A, B, C, E, G, I, in this graph of 9 vertices, forms a subset of all the vertices such that it's a dominating set. So this is a dominating set thing. So if I give you a graph, and if I have a graph and I want to compute a dominating set, then this is called dominating set problem. There could be multiple different dominating sets. This is another dominating set. So if I select B, D, F, and H, this is also a dominating set. So we say a minimal dominating set is a dominating set such that the no proper subset of that set is also a dominating set. So if you look at this graph, if I remove the vertex D, then the remaining set D is still a dominating set. So this is not a minimal dominating set. So I can say that if I look at this set, this is a dominating set. This is also minimal dominating set. It's also a minimum dominating set. So we define another problem based on dominating set, which is called the upper dominating set. So what is an upper dominating set? An upper dominating set is basically a minimal dominating set of maximum cardinality. So there might be multiple different dominating sets, and there might be multiple different minimal dominating set. And if we choose a dominating set which is minimal and which has the maximum cardinality, then that is called an upper dominating set. For example, if you look at the same graph with two different dominating sets, both are minimal dominating set because we cannot remove any vertex from this dominating set. Therefore, they are minimal dominating set. But the set on the left-hand side is an upper dominating set because this one has a maximum cardinality. It's maximum cardinality. So in a given graph, in a given simple graph, the upper dominating set is a dominating set of, it's a minimal dominating set of maximum cardinality. Upper dominating set problem is generally an NP-hard problem. So it's generally very difficult to compute an upper dominating set. So it's generally an NP-hard problem. And it's not just NP-hard, there are other discouraging or pessimistic results. For example, from a parameterized complexity perspective, it is W1 hard. So W1 hard are the problems for which we cannot come up with, and we cannot come up with a parameterized version of this problem. So we cannot parameterize it. So if you're familiar with parameterized complexity, you can appreciate it. So last semester, one of my students, MSS students, did his thesis on parameterized complexity, parameterized algorithms, and he discussed this problem as well in his thesis. And not only that, we also have a discouraging result that it is also hard to approximate it. So unless P equal to NP, finding a good approximate solution for this problem is hard. So this is usually a common thing with hard problems, that many hard problems come in this fashion, that unless P equal to NP, finding a good approximation is also hard.
So in this case, what by approximation of upper dominating set?
Approximation means that, for example, so you have an idea about approximation algorithms, right? So for example, if we have a problem, and that problem is about graph problem, for example, a Gaussian graph problem. For example, if I give you a planar graph, then we know that every planar graph can be colored with at most 4 colors, right? So this is very well known. But coming up with, for example, if I ask you, is it possible to color the graph, color the vertices of the graph with 3 colors? It's NP hard. And it's actually NP complete. So it's not possible for us to come up with a polynomial algorithm which can do it. So approximation algorithms are those algorithms which try to solve the NP-hard problems in polynomial time, where the result that we get is as good as possible, not necessarily the best answer.
What do you put here? Yes.
So in this context, the approximate answer would be that given a graph, we want to come up with an upper dominating set. And so as the result, we would get a dominating set, a minimal dominating set, but it is not necessary that we will get a maximum cardinality dominating set.
But it should be, at least there should be some comprehension that is maximal in some approximate sense.
Yes.
So I think the question is, what is that concept of approximation, of being maximal in this case?
See, so the concept of maximum or maximal in terms of approximation is that it will give you an answer that we would think or assume it's maximum, because we have no idea and no way to verify whether that is a correct answer or not. So since we are talking about the approximate answers, right? So it will be an answer, and we cannot find any better answer otherwise in a reasonable amount of time. So that is the sense of approximation. So it will give us an answer, which is, okay. So I can explain it this way, that optimization problem comes in, problems come in 2 different flavors, either minimization or the maximization, right? So if we have a minimization problem, then the approximate answer will be worse than the original answer in a sense that it will give us an answer which is bigger than the expected value. For example, if the optimal value of something is A, then it will be something A plus some number, right? So because we are trying to minimize, so we will not get the minimum. So it happens the other way in the maximization problem. So if you want to maximize something, and we have an approximation algorithm for a maximization problem, it will give us an answer which is less than the optimal value. So in this case, if we have an approximate algorithm which computes the upper dominating set problem, then it will give us a set of vertices which might not be the true upper dominating set. So it may be of lesser cardinality than actually what actually is the optimal.
It won't be actually upper dominating set.
It will still be, it will be a dominating set. It will be a dominating set, but it may not be the upper dominating set, right? So approximation, जब भी हम करते हैं, so we lose some information. Right, so it's hard. So we have actually there are some fundamental results in approximation. That is, that if you have an NP-hard problem, then usually finding a good approximate solution is also very hard, unless P equals 1.
So I suppose there would be some parameter which will control that how far you are.
How far we are from
the true solution.
Yes. So usually we measure the approximate algorithms in multiple ways. For example, we measure that. So for example, if we have an approximate algorithm, we definitely, we know that the actual problem is NP-hard. So we cannot solve that problem for large values of graphs or large values of input, right? But we can solve them for smaller values of the problem. So what we do, we solve the optimal version for the smaller values, and we apply this approximation algorithm on those smaller things, and we compare the results and how bad it is. So we have ratio of the solution. So we have in the maximization problems, we have one ratio, and for the minimization problem, we have the other ratio. So we have ratios that how bad it is. So sometimes those ratios are ideally we would be looking at constant ratios. So for example, if the answer is n and approximation gives me 2n, it's fine. It's the ratio is constant. But sometimes the ratio is polynomial. Sometimes the ratio is exponential, and so on and so forth. So we want to have a ratio as small as possible. A constant number, which is a small constant, is something that we 1.5 or 1.2 or 2 or something like that. So we know that we are not far behind from the actual answer. But again, these are just the ratios, which are the expected ratios, not necessarily the exact cases. So this problem, the upper dominating set problem, it makes that, I mean, it is hard from the point of view of approximation unless P equal to NP. And this is usually the case with most NP-hard problems, that unless P equal to NP, we cannot approximate. This problem has other side, which is that this problem is easier to compute in some classes of graphs. For example, this problem can be computed easily in polynomial time for bipartite graphs, for example, chordal graphs, generalized series parallel graphs, etc. So these are some special cases where
the approximate methods may, you don't know beforehand that what is the upper dominant set of the graph. How do you know that your approximate method is going to converge to upper dominant set or a maximum set?
So what we do, we try to figure it out on smaller graphs. So NP-hard does not mean that we don't know algorithm.
There has to be a proof that this algorithm converges to some approximation which is not upper dominating exactly. But you can't do examples, right? Let's say if you start with some lesser number of vertices, and your method gives you upper dominating set.
Yes.
And then you start another set of vertices, gives you maximum set.
Yes.
Right? This is not a proof.
Of course, this is not a proof. So when we do this, when we give the proof, we give a proof. The actual proof, not the examples. Examples are to clarify what's happening.
Yeah, but that's my question. Then how do you know that the approximation is going to converge to some approximation of upper dominating set or the maximum set?
Because that's what I started talking about, that NP hard does not mean that we don't know the solution. It's that it's too hard to find a solution in any given reasonable amount of time, right?
Yes, I understand that if give us, but there's a question of existence and right. So
No, but you can have some parameter and you can show that for some value of the parameter, what you are computing will be the solution. It's just that if you take exactly that value of the parameter, the computation becomes hard. So it's like a perturbation in that parameter, right? So for other values of the parameter, you can do some computation and you can show through a mathematical proof that for the final value of the parameter where you cannot compute, you will have the correct solution. So then this becomes like a expansion in that
Yeah,
parameter.
that is my question. Yes, there should be a proof, right?
Yes, there is a proof, but that's not very simple, right? So I'm just mentioning here that this is a hard problem, even from the
So
approximation
you
point of view.
first mentioned that you take some examples and see where it converges and you from there the extra.
No, I don't get your question. So what's your question?
I got it.
I did not get it.
My question was that you start with an approximate algorithm, right? Say that you can't compute, it's very NP hard problem. So you look for an approximate algorithm, right? And that algorithm will give you a solution which is not exactly what you're looking for.
Yes.
It will be an approximate of upper dominant set.
Yes.
My question is, how do you know that your algorithm will converge to a solution which is an approximation of what you're looking for? There has to be some proof.
Yes, of course there's a proof, but I'm not showing the proof because that's not many sense, right? This is already known. It's a well-known thing. But the other point is important that in some special cases of graphs, this problem can be solved in polynomial time. For example, if I have a bipartite graph, then it's easy to compute. Okay? And there are some other examples. So the main contribution of my research and the things that I would talk about are some NP hard results, NP hardness result, and one dichotomy result, and a boundary class result. So I will just mention it here, and then once we are over there, I will explain a little bit more, but I won't go into the proofs. So there are two hardness results that we publish, and that is the problem is NP hard for complements of bipartite graph. So we know generally it's NP hard, but it was not known whether it is NP hard for these classes of graphs or not. So this problem is NP hard for complements of bipartite graphs and for planar graphs with vertex degree at most 6 and girth at least 6. I will explain what is the degree and what is the girth of a graph. The second result, the problem admits dichotomy in monogenic classes of graphs. So what does it mean? I will explain that what is a monogenic class and what do we mean by the dichotomy result. As I explained, that the upper dominating set problem is NP-hard in general, and it is also polynomial time computable in certain classes of graphs. So it was not known what is the boundary where we see that if we change the classes of graphs from one particular style to the other, then the problem becomes NP-hard. We clearly know that it's polynomial computable in certain classes. It's NP-hard in other classes. So the contribution is that we found some other classes for which it was NP-hard, and we also found the boundary from where if you jump to the other side, this becomes the NP-hard. If you're on one side, you can solve it in polynomial time. If you go to the other side, it cannot be solved in polynomial time. And we did not just show that dichotomy exists. We also showed that what is that boundary which creates this dichotomy. Okay. So before you came, there was a dichotomy of all math faculty here and CS faculty over there. So you broke that boundary. So Tahir was mentioning it. And so we found that boundary, right? So, so some preliminaries. So all the graphs that I would consider in this talk and also in the paper are simple graphs. That they are undirected graphs and which is without loops and other things. So we define the girth of a graph G as the length of the shortest path in the graph G. So if I can find a cycle, the length of the cycle, shortest cycle is the girth of the graph. So K sub n, P sub n, and C sub n denote as usual is the complete graph, the line graph, and the cycles. So CN means the cycles of n vertices, K means the complete graph of n vertices, and PN means that line graph of n vertices. So I also define what is 2K2. So we know that K2 means the complete graph of K vertices, which is this. So 2K2 is the disjoint union of two copies of K2. Okay, so 2K, this is K2, and this is 2K2. So it's a disjoint union of two copies of K2. Okay, so if I say that G is a graph and U and V are two vertices, and if U is adjacent to V, we write UV, okay, and we say that they are neighbors. The neighbor of the entire neighborhood of a graph of a vertex V is denoted as n of V, and degree of V is the size of its neighborhood. So for example, if a vertex, if there's a vertex here, V, so this vertex V has 5 vertices, 5 other vertices which are adjacent to it. So the neighborhood of V here is, for example, it is A, B, C, and D, A, B, C, D, and E, and size of the neighborhood is 5. So the cardinality of the set is the size of the neighborhood, and this is also the degree. And if the degree of each vertex is 3, then we say it's a cubic graph. So at any time, if you have questions, please tell me. So we say that a subgraph of G is spanning if it contains all vertices of G, and a subgraph of G is induced if two vertices of the subgraph are adjacent to each other, if and only if they are adjacent to G. So is it clear? Okay. So we say that a graph H is isomorphic to induce subgraph of G. We say that G contains H, otherwise we say G is H. So what do we mean by isomorphic? So if we have two graphs and there exists a homomorphism from a graph G1 to G2, and if that homomorphism is bijective, then that homomorphism is isomorphism. So we say that H is isomorphic to an induced subgraph of G. So there's a graph G, and there's inside G, there's an induced subgraph. If H is isomorphic to that, we say that G contains H. Otherwise, G is called H. Yes.
So what do you mean by homomorphism?
Homomorphism means, how should I say? We can think about homomorphism of graphs as the renaming. One crude example is the renaming of vertices, for example. So for example, so not all more, so isomorphism is a renaming of vertices in which the relationship is bijective. So for example, if you can rename a vertex A as 1, then you can rename 1 as A backward as well. So it's bijective. So for example, if I have this graph, so these two graphs are basically isomorphic. So for example, if it is A, B, and C, this is 1, 2, and 3. We know that there exists a mapping of vertex A to some vertex here, and there exists a inverse mapping as well. So this homomorphism is bijective. So not all homomorphisms are bijective, but if the homomorphism is bijective, it's called isomorphism. So isomorphism of two graphs is basically renaming of the vertices in such a way that it preserves the structure.
Homomorphism means you're preserving structure.
Yeah, we are preserving structure.
I thought that the shape doesn't matter. It's just about how the nodes are connected. That's
Yes,
what
yes,
makes the graph.
exactly.
So, but homomorphism usually means that you preserve some structure. So my question is, what is the structure which is being preserved under this?
The structure in isomorphism that we are trying to preserve is the, first of all, both these graphs must have the same number of vertices and same number of edges. And if a vertex is connected to a vertex in actual graph, then it should be connected in the isomorphism as well. So for example,
can it still look different if you preserve all of this?
Yes, they can look different. For example, So these two graphs look different, but they are isomorphic. It's a very simple example, but we can have a very complicated, we can have very big graphs which look very complicated, and they may not have to be planar, but they can still be isomorphic. So over here, I'm trying to say that if we have a graph G, and in this graph G, there is a subgraph, and another graph H is isomorphic to that subgraph, induced subgraph, then we say that G contains H. Otherwise, we say that G is H-free. So this concept is important, which we will use multiple times. For example, this graph does not contain a cycle of 3 vertices, right? So this graph is free of C3. So this is C3, and if this is G, then G is C3 free. This graph does not contain C3. But if I had this edge here, then this graph has an induced subgraph which is isomorphic to this graph C3. So we would say that C3 is isomorphic to some induced subgraph. So this graph G contains C3. But if I don't have this vertex, this edge here, then this graph is C3 free graph. Okay. So given that, so it is not, it's not that we just do it free and containing just one graph. You can have multiple graphs which can be there, right? So we said that given a set of graphs, and so let's say we have multiple graphs which are in the set N, then we denote free Fn the set of all graphs containing no induced subgraphs from it. Okay? So for example, if I have this graph, let's say I have an infinite, or maybe let's say 1 million vertices which are in this graph, then this graph is C3 free, this graph is C4 free, this graph is C5 free, and so on and so forth, because this graph does not contain any cycle. So I can say that M contains all of this. So M contains, let's say, M contains C3, C4, and so on and so forth. So I can have multiple graphs. I can have multiple graphs in N. Then we say the free of M is the set of all graphs without any of these graphs from M. A class of graph, or a property, a graph property, is a set of graph which is closed under that property. Okay, closed under isomorphism. Okay, so we say that a class is hereditary if it is closed under taking induced subgraph. We say that a class X is hereditary if and only if X is free of M for some set N. And if M is finite, we say that X is finitely defined. And if M consists of a single graph, then X is called monogenic. So this is one type or a class of graphs which I used in one of my results, which was about the, initially when I talked about this type. We say a class of graph is monotone if it is closed under taking subgraphs, not necessarily induced subgraph, and every monotone class is hereditary. So what do we mean by hereditary graphs? Or it's a graph property. For example, if you have a class of trees, class of bipartite graphs, and so on and so forth. So this is the graph property, right? So if we have a class of, then we say that this is a hereditary property. So if I have a class of all bipartite graphs, then every graph is similar to the other graph in a sense that they are all bipartite. So there is a common theme among those graphs. So they are hereditary. Okay. So a clique is basically, we know it's a complete subgraph of a graph, or in other words, we can say it's a pairwise, it's a subset of pairwise adjacent vertices. An independent set in a graph is a subset of vertices such that no two of vertices in that set are adjacent to each other, right? So for example, given this graph, I can select this vertex, and this will form an independent set, right? And each individual vertex of the graph forms an independent set as well, right? So this vertex is an independent set in this graph, right? And so on and so forth. So usually when we talk about independent set, we want to find out the maximum independent set, because finding a minimum independent set is trivial.
In triangle, that is adjacent to the group.
No, the independent set, so this, let's say this is A, B, and C. I would say independent set contains A. This set contains only one vertex.
But A is adjacent to B.
No. All the vertices in that set are not adjacent to each other. How many vertices we have here? One, right? So by default, it's the trivial solution. It's the trivial, every graph, if you take any graph and take a vertex of that graph, that forms a trivial independent set, right? So that's not what we want. We want a maximum independent set. So in this particular graph, we cannot have an independent set of more than two. So if I select this one and this one, these two are not adjacent, right? If I add any other vertex, this will no longer be the independent set. So this is both maximal independent set as well as maximum independent set, right? Okay. So this is an optimization problem where we have to find the maximum solution, not the minimum. Anyway, so independent set is a set of vertices given a graph, the set of vertices such that no two vertices in that set are adjacent to each other, right? Similarly, a graph is called bipartite. So there are multiple definitions of bipartite. For example, a bipartite graph is a graph in which you can divide the set of vertices in two vertices, so, two sets of vertices which are such that they are disjoint. Or you can define the bipartite graph as the graph coloring problem. If all the vertices of the graph can be colored using exactly two colors, then this is also bipartite graph. So over here, I give another definition of bipartite graph. We say that graph is called bipartite if and only if it's free of odd cycles. Okay, because every bipartite graph should not have odd cycles. So it should not have a cycle of size 3 or 5 or 7 or 9 and so on and so forth. So that means the bipartite graph. So we say a graph is called co-bipartite if the complement of the graph is bipartite. Okay, or in other words, it's free of C3 complement, C5 complement, C7 complement, and so on and so forth.
What's the complement?
Complement of a graph is a graph in which two vertices are adjacent. So given a graph G, the complement of graph G is G bar, is a graph in which two vertices are adjacent if and only if they are not adjacent in G. Okay, so we say independent set is maximal if no other independent set is the set properly contains I, and every maximal independent set is a minimal dominating set. So we can prove it. It's very simple. I'll show the proof, but we don't have to go into detail. It's very straightforward. So if I can find maximum independent set, I can also find a minimal dominant. Okay, so let's talk about boundary classes of graphs. Assuming that P is not equal to 20. Okay, so this is the basic requirement over here. So let pi be an algorithmic graph problem for such as maximum independent set or upper dominating set problem and so many other problems. We say that a hereditary class X, so we define what is a hereditary class. So a hereditary class X of graphs is pi tough, capital Pi tough, if the problem is NP hard for graphs in X and pi easy otherwise. It's a very simple definition. So for example, if I have a class of graphs, okay, if I have a hereditary class of graph X, then we say that a problem, an algorithmic problem is pi tough if it is NP hard for those problems and pi easy otherwise. So we say that a hereditary class X is a limit class for pi if X is the intersection of sequence of pi tough classes. In which case, we also say that the sequence converges to X. So this requires a little bit a little explanation. I'll try to give as simple explanation as possible. So let me go to another slide and then maybe I will come back. Okay. So, for example, if I consider the maximum independence set problem, then it is known that maximum independence set problem is NP-hard for graph with such that the degrees of the graph is at least 3. Okay, so this is NP-hard problem. So what we can do one thing in this graph. For example, so for example, if I say that my graph is C3, C4, C5, and CK free. For example, I don't have any cycle of length 3, cycle of length 4. So cycle of length 3 because it's the smallest cycle. So if I don't have any cycles up to length k, then this is the graph which is up to CK free, right? So it means that this graph is of large grid, right? Now if I say that if k is up to infinite, then I say that so let's say if this graph is G, then G is cycle free. So this G does not contain any cycle. Okay. So if the graph does not contain any cycle, then we can have so we know that what kind of graphs do not contain cycle? A tree does not contain a cycle. If I have multiple trees, and all those multiple trees are not necessarily connected, they could be disjoint. It means that G is a forest. Okay? G is a forest. So we said that the forest is a limit class for the maximum independent set problem. I will explain what do we mean by that. So forest is a limit class for the maximum independent set problem. So that's exactly what I'm trying to say here. The hereditary class is a limit class for pi if pi is the intersection of the sequence of all of these things, which are pi terms. So for example, every graph that we will have in this forest, it would be hard to compute maximum independent set, right? And we can prove it by changing these graphs. For example, if I have a graph in which I have vertex, then I can convert this edge into, I can subdivide this edge as this. That is, for every edge that I can find in this graph, I can subdivide this edge as this. So I can insert another vertex between two vertices. If I do it for one edge, okay, then I know the size of the maximum independent set. For example, if this was some part of a graph G, and I did it for one of the edges, then it will increase the size of the maximum independent set by exactly 1. Okay? And if you do it sufficiently many times means that we can do it for k times, such that the number k is polynomial within the number of vertices, then we can be sure that the maximum independent size problem will increase, and it will also increase the girth of the graph, because this way we can increase the cycle length, right? Because if there is a cycle here, for example, 1, 2, 3, 4, so it's a C4. If I do it for one edge, the cycle length will change from 4 to 5. If I do it for another edge, it will change from 5 to 6 and so on. And I can keep doing it. If I can keep doing it for sufficiently many times, such that that number still remains within the polynomial limit, that is the polynomial number of, if it is a polynomial within the number of vertices of the original graph, then I can show that I have destroyed all small cycles. I can destroy all small cycles. But the thing is that if the original graph G is a graph such that the maximum degree of the graph is 3, then still it will be the maximum degree of the graph. So we are not changing the degree of the graph. So if the original graph is NP hard, if it was NP hard to find the maximum independent set in G, then even after this, it will be NP half. So this is a limit class. This does not prove that this is the minimal limit class, but it proves that this is a limit class. So the proof for the minimum limit class is a little bit involved, but I assume that we would agree, you would believe me. But this is also a minimal limit class. And, and this limit class, minimal limit class, will be used later on in some other results. So, for example, this is the cycle of length 4. This is a special kind of graph, which we call the H graph. This is the length of this H graph is 5 because we have 5. So this 1, 2, 3, 4, and 5. So this is the length of this H graph. So it will be used later on. For example, if I say that, so I define a new class, this ZK, and I put it in bracket, that actually shows that it's a kind of arbitrary class. So because it's impossible to distinguish a property of within those classes, so it's some sort of equivalence class. So the class ZK of graphs is the class which are C3, C4, C5 up to CK, that we do not have any cycles up to length K, and we also do not have H graphs of length 1, H graphs of length 2, and so on. So what are those H graphs? These are the H graphs that I just showed. So these are kind of H graphs. So if I have a graph, a class of graphs in which I do not have any cycles, and I also do not have H graphs, then that is called the ZK graphs. It's such that the degree at most 3. Okay. If I have those sequence, for example, Z1, Z2, Z3, not Z3, C3, Z4, Z5, and so on and so forth, this converges to the class of forest. As I just showed, that if we can convert it into a forest, such that every connected component is basically a kind of tree, and that kind of tree will look like this. Right? So it's a kind of tree. Okay, and if you have multiple such disjoint components, they will form a forest. Yes.
The proof says convergence show that you use some kind of metric, like either all sets, right? They converge to the other set. How do you check a convergence? Doesn't show that. They say a number, the sequence, and you will gain distance of that. But if you're
We are not talking about any topological or geometric interpretation.
Proof made, how do you ensure the convergence?
It's dependence that you have a sequence of containment. It's defined to containment.
So you will find a point after which there is no change. So it means it converges to that point. Right. So how do we say that it converges? Since it's not an arithmetic sequence or we don't, okay.
But there's some kind of metric of generalization. It doesn't have to be could be anything.
No, I'm not. That's exactly what I said. Okay. We do not care about topological or geometric properties. Euclidean distance की बात नहीं आएगी, किसी और distance की बात नहीं आएगी, because we are not interested in geometry or the topology of the graphs. We are treating graphs as a discrete object. So whatever their orientation or geometry is the graph. So we are only talking about the size in the kind of the graphs. So graph is that. So we say that eventually they will converge to a forest, right? So if you keep doing it, if you do it sufficiently many times, then it will become a forest. And forest will look like this. Right? So this is a tree. Every tree would have something like this. So we call it SIJN graph, or the form of this graph. Okay, so we say that minimal with respect to set inclusion, limit class for the problem pi is called a boundary class for pi. Okay, अभी जैसे हमने limit class की बात की थी, so we call that limit class a boundary class. So limit class is basically a sequence of those things. So if we consider all of them, this is called a boundary class. So we have one result which says that if P is not NP, then a finitely defined class X is part of if and only if X contains a boundary class for pi. Okay. So this result will be used to come up with other results. So if you are interested in the proof, I have the papers, I can give you the links. So I'm not going to prove it. So we have a sequence of lemmas, which we will use to prove other results. So if X is a finitely defined class containing a limit class for NP-hard problems, NP-hard problem pi, then X is pi. So I think it's obvious from this theorem and the definition. So the minimum dominating set problem is NP-hard in the class dk for each fixed value. Okay. So now we are trying to create a connection between the dominating set problem, the minimum dominating set problem, and the maximum independent set problem. So if you remember, I said that maximum independent set and minimal dominating set problems are connected. So we say that the minimum dominating set problem is NP-hard in the class dk for each fixed value of k. So if you fix the value of k, the k could be 3, 4, 5, 6, 7, any positive integer greater than or equal to 3, then this is it's NP-hard for such things, right? So you can imagine what is Z4, Z5, Z6. So it could be a forest, right? Kind of forest. The class S, this is the calligraphic S, is the boundary class for the minimum dominating set problem. So I say that this class S contains all those graphs, which we call the boundary class for the minimum dominating set problem. So we will use this later on. And this is the first result, which I showed initially, the main contribution. So this is one contribution over here. The upper dominating set problem is just if I restrict it to the class of planar graphs with minimum vertex degree 6 and girth at least 6, then this problem is NP-hard. So if I say that I'm trying to compute upper dominating set problem in a graph which is planar, such that the degree of each vertex is at least 6 and the girth is at least 6. So it means that the length of the minimum cycle is 6, then still this problem is NP-hard. Okay, and later on we will show that it will create a kind of dichotomy. So the upper dominating set problem restricted to the class of complements of bipartite graph is also NP-hard. So if I have a bipartite graph, I know what's the complement of a bipartite graph. So finding upper dominating set in complement of bipartite graph is also NP-hard. Remember, initially I told you that finding upper dominating set in a bipartite graph is polynomial. It's not NP-hard, but in the complement of bipartite graph, it is NP-hard. Okay, so I will create two special kinds of graphs, and I will use these graphs later on in some result. For example, if I have this P4, so P4 is basically a line graph of 4 vertices, right? Every vertex is connected to the other. So we say that S of G, so if this is P4, then this is S of P4. So S of a graph for any given graph G is an induced graph of G. That is what we do for every edge that we find here, we create a vertex for that edge. So you can imagine there's an edge here, so we create a vertex. So there are 3 edges, so we create 3 vertices. And once we create new vertices, we connect the original vertex, which are blue, to these new vertices, which are black. So if we do it for every possible graph, then it is called the induced graph or S graph. Really simple idea that given any graph, if I create a vertex for each edge and create these new edges, then this is called the induced graph or the S graph. Now with this S graph, if I do one more thing, then this becomes Q graph. For example, if I make these S graphs as the cliques, for example. So this is clique because every vertex here is connected to every other vertex, and every vertex over there is also connected to each other vertex. Then we call it a Q graph. And we can do it for every graph G. Okay. So this is an example of graph P4. So this is P4 and this is Q of P4. Okay. So if I create S of some graph, we can clearly see then these vertices, if I select only these vertices, this is an independent set. If I select these vertices, this is also an independent set. Right? So these two sets are independent. So, so if I say that V is the original set of vertices, and E is the new set of vertices, which I created from the edges. Then these two sets are basically the independent sets. Okay, and once we have these independent set, I can create an S graph of a G, a graph G. Then from that S graph, I can construct a Q graph, and Q graph is just the creating the clique or the complete graph of those independent sets. Okay, so we know that the upper dominating set, it is not moving from here. The upper dominating set problem is NP-hard in the class of complete graphs and blah blah. So we say that a boundary class for upper dominating set problem consists of graphs obtained from the graphs consists of graphs Q of G obtained from the graph. Can you move? Just go down. Maybe peaceful. This one. So we know that upper dominating set problem is NP-hard in the class of complements of bipartite graph. So we say that boundary class for the upper dominating set problem consists of the graphs Q of G obtained from the graph G in S. What is this S? S is the limit class for the maximum set problem, right? So if I have all simple graphs G represented in the calligraphic G class, then Q of G is the set of all Q graphs of the class of simple graphs. We define Q star of X as the hereditary closure of Q of X. So it will be required in one of the results, which are obtained by Q of X by adding all induced subgraphs. So for example, this closure is defined as including all induced subgraph of a graph in a class, so that will be Q star of X. Similarly, we can define S star of the hereditary closure of S of X. So I have a couple of lemmas, and based on those lemmas, so these are not very important, but we would use these lemmas to prove this lemma that, for example, I can say synchronize this. Okay. So if G, this calligraphic G is the set class of all simple graphs, then we say that Q star G is free of N, where N, so this is our result. It says that free of N, where N is a set of 11 subgraphs. So 3 of them are C3 complement, C5 complement, and C7 complement. That is the complement of cycle of vertices, 3 vertices, complement of cycle of 5 vertices, and complement of cycle of 7 vertices. So these are 3 different graphs. And we have 8 more graphs here. So this is a claim that the hereditary closure of Q graphs of all simple graphs is free of all of these graphs. So if I take any simple graph, any undirected simple graph, and I find Q star of that, then that graph will be free of all of these things. Okay, so from this we can create a kind of limit class and the boundary class. So this is the main result of the paper, which says that if P is not NP, then Q star of all graphs in calligraphic S, which is the limit class for the maximum independent set, is a boundary class for the upper dominating set. In simpler words, the hereditary closure of the limit class for maximum independent set is a boundary class for upper dominating set problem, provided P is not NP. So this is the main result which we found.
So these boundary classes exist for any NP-hard problems?
That's very interesting. Actually, no, they don't. We only know a handful of problems for which we can find boundary classes. And this is one of those problems for which we were able to find boundary classes. So yeah, so they do not exist. I mean, they may exist, but we don't know. We only know for a few of those problems. Okay, and what is the dichotomy result? It was published, it was the first paper that we published back in 2014. The upper dominating set problem can be solved for P4 free graphs in polynomial time. So what is P4 free? So if I have a graph which does not have P4, so for example, this is the P4, this is the P4. Any graph which does not contain P4, then upper dominating set problem can be computed in polynomial time. So it will no longer be harmful for that. And there's another result which says that if not only P4, but if I have a graph which does not contain two disjoint copies of K2, which I initially explained that this is K2, this is another K2. So together we can call it 2K2. So if a graph does not contain two disjoint copies of K2, then it is again possible to compute upper dominating set problem in polynomial time. So we call it H-free graph, right? So if H is 2K2 or P4, then we can compute it in polynomial time. Otherwise, it's like that brings us to the final conclusion. And so there are basically two things that we identified as first boundary class. So it was unknown for this problem, and it is unknown for most problems. Only few problems, have boundary classes. So it was possible first to find an upper dominating set problem, a boundary class for this one, and we proved that the problem admits a dichotomy for monogenic classes. And these are the three papers in which these results were published. So this one is the first one, then second and third one. So these two are conference papers. And the first one, which is on the top, which was published in 2017, is in Algorithmica. And that's all for my talk. Thank you very much. If you have more questions.
कन्वर्जेंस प्रूव करने के लिए जैसे इसमें because after all the graph is a set of vertices and connectivity, right? So do you use any bigger theoretic results? Because maybe हम set की convergence sequence of set की convergence को prove करते हैं, इस तरह की चीज आप यूज करते हैं?
नहीं, इसमें यूज मेजर थ्योरी यूज this problem.
So yeah, so my question is that this problem of so what you were calling, what was it, the maximal dominant
Upper dominating set problem.
maximal upper dominating set. Can you say like what's the relevance of this problem in general? Is it important in some context, or is it like just as an example of analyzing these anti-hard problems? What's the relevance of this problem?
Actually, when I started working on this problem, I did not know there is any application. And probably there is no application, or at least I'm
not saying application, I'm saying relevance.
Relevance from the particular.
Relevance, like if you are studying something, like in any field, there could be trillions of problems. I can just pick anything. Yes. But there's some problems they are considered interesting because they say a lot of things about that subject, or they have connection with other subjects. So in that context, why is this problem interesting? To me, it looks like the way you presented that one could think would be that because it gives you an example of finding a boundary class for an NP-hard problem. So is it just that, or is there more to it?
So actually, we started with this problem back in 2013 or 2014. And we started with a very simple idea that upper dominating set problem seems an interesting problem. There were some applications, but it seemed interesting. And we found that we were working on it. We found that that in general it is NP-hard, but the last two results that I showed, this result. So we found it. Okay, if I have a graph which is P4 free or 2K2 free, then it is polynomial solvable. So at that time, one of my co-authors, who is a professor at Warwick, and he's a graph theorist, very well-known graph theorist, he started working independently on this problem, and he got an idea that because he already worked with other problems, some other problems in graph theory in which he tried to find boundary classes. He said that maybe there's a possibility, because this problem shows a dichotomy, then there's a possibility we can find a boundary class for this problem. So he started working in it, and eventually we collaborated and we found some results. So the relevance of, we started working on this problem not because we wanted to find boundary class, but we thought it's interesting. It looks an interesting problem, and we started working, and we thought that we could come up with some interesting results, and we found some interesting results. So we found dichotomy in that. And once the dichotomy was formed, so independently we started thinking about a boundary class. Now the relevance of this problem, I think there's only importance or relevance is that it seemed interesting to us at that time.
Well, when you say that it seemed interesting, then there has to be some reason.
Mathematically interesting, that's it.
But even in mathematically interesting, when some problem is interesting, it's usually called interesting because it's interesting to a lot of people. And there are reasons why it's interesting to a lot of people. So, like you said that, like I can see one thing, like you found that this is an example of finding of a problem where you have this boundary class. So in that context, yeah, I find it interesting. But usually when you say a problem is interesting, it cannot be like you just thought it's interesting. Even when you say it's interesting, you have to give some reason.
Yeah, okay. So there's a non-scientific reason behind it as well. So actually I was working on a PhD problem which has nothing to do with graph theory. I mean, I use trees and some other kinds of graphs in it, but it's not a graph theoretic research. And I had been working on those problems for quite some time. I think by that time it was already 4 or 5 years that I've been working on it. And I wanted to switch for some time to work on something interesting outside my domain. So it was the first problem that I found, and it seemed interesting from that point of view. It's not what I was working on it for 5 years. So that's one reason. So I switched to it. Later on, we found that, okay, it's interesting from that point of view as well. Yeah, but there was no insight or no incentive to work on this particular problem and not anything else. It was pure accident that I worked on. Does it satisfy?
Yeah, I mean, so your advisor suggested.
No, so my advisor was very fixed on those problems which I've been working on, right? And so this graph theorist professor, he was visiting our school, and he's a friend of my professor. He was visiting my professor, and they were working on something else. And I knew that he's a graph theorist, and I went to him and I said, okay, I'm also interested in graph theory. So let us work on some graph theoretic problem. He said, okay, I just found one interesting problem and I started working on it. So let's see.
So that's the answer. I mean, if a graph theorist finds it interesting, then he must have his reason.
Maybe.
And as you said that then this other guy started working on it.
Yeah.
So that shows that this is something they care about.
Yeah. I mean, if I look at all the historical events around this thing, they're very interesting because that problem, his name is, I will show you.
Can you also say like how well it was received, like this result?
How well it was received? Okay, so this is the conference where we first published. It was in Conference on Combinatorial Optimization Application. I attended this conference. I did not present it. I attended. And I was there when this professor Wadim Lozen, presented. And I found that people were not very interested in this problem. And there's actually a problem in the sense that in mid 2000, from I think 2010 and onwards, people are more interested in parameterized complexity issues. So what is parameterized complexity? So we know that many interesting problems are NP-hard, right? Most of the optimization problems that are interesting are usually NP-hard. And we cannot do much about it because if they are NP-hard, unless we know P is equal to NP, we cannot do much about it. So there's a new field which emerged I think in late 1980s or early 1990s, which is called parameterized complexity. It's a completely brand new field. This parameterized complexity theory deals with those NP-hard problems which can be done in polynomial time with certain parameter. For example, we can change the complexity of this problem in such a way that, so for example, if I gave you, I don't remember exactly what it is, but suppose there is a graph and we want to find certain property of that graph, for example, clique or the vertex cover or the independent set, or so on and so forth. Usually finding such thing is NP-hard. But if I can parameterize it, parameterize this objective function that I want to find out, and that parameter is usually not a big number. We call it a k parameter. And if that number k is not hard, even if there is an exponential component of that k, for example, 2 power k, in the time complexity analysis of the algorithm, if k is not large, then 2 power k is also not large. The remaining thing that we have about the problem can be done in polynomial time. So that's a new field of parameterized complexity algorithms, which started in late 20th century. And people are more and more going towards that. So I remember when this problem was presented, a couple of people in the audience, they started pointing out, did you work on parameterized complexity, and how is the parameterized complexity version of this problems are going, and are they easy to solve, and so on and so forth. We knew at that time that there exists a parameterized result, and it is W1 hard. So W1 hard is a classification of parameterized problem, which means it's hard. Even from the point of view of parameterized complexity, it's hard. So we cannot do much over there. So it was not very well received in that sense. So people were more interested in finding some applied sense of this problem, which we could not.
So I mean, after the publication.
After the publication, since this problem itself is mathematically rich in the sense that the results are good, and we were able to find dichotomy result in the first paper, and then later on we were also able to find the boundary property, right? This boundary class, which is, and since only handful of problems have boundary classes, so it was well received in that sense that it adds on to some theoretical understanding of graph theory, but I think not more than that. So not very well received, as is the case with most theory things. But it was published in a very well reputed journal, Dominica. Any other questions? Did I sense? Yeah. Any other questions? Okay, thank you very much. Thanks a lot. Hope you like it. If you are interested, I can send you the papers, which contain proofs and more details. Sure, please. I want to hear a